Hello, my name is Scott Marshall, and I'm excited to be here today virtually to tell you about the SCEC community fault model. Let me put on my pointer and some of the associated tools and resources that you can use to use this great product. So on behalf of my co-authors, Andreas Plush and John Shaw, we hope that you find this interesting. So I have to point out that SCEC has a series of community Earth models. The fault model is not the only model. We have a fault model, a geodetic model, a rheology model, a stress model, a thermal model, several velocity models, and a software framework that delivers velocity models in a unified manner. So SCEC is not developing just a fault model. We have a whole series of models. We even have some databases that I'll talk about later. I also have to point out that this is a screenshot of the SCEC homepage as it is right now, that we would not have many of the wonderful tools that you're going to hear about today if it wasn't for the great SCEC IT web team, which is Tron Nguyen, Phil Mecklin, who's now retired, but developed a lot of these tools, with Edric Pak and Mei Wee Su. Mei is our primary community models developer. So the web-based tools that I'm going to show you have been a collaboration between myself and Mei, and she's just fantastic. We're so glad to have her. With the community fault model and all of the community Earth models at SCEC, we strive to meet what are called FAIR principles. And FAIR principles essentially are listed over here. I'm not going to go into the huge details, but basically want all the models to be findable, accessible, interoperable, meaning that you can use them in your workflows, and reusable. Do we have enough documentation so that you can use these models in a variety of ways and maybe even build on them? So how do we accomplish this? Or at least I hope we've accomplished this. This is a screenshot of the SCEC homepage again. And so we hope that the easiest way for you to find them is simply to go to scec.org and click on research. And so if you click on research over there, a little menu pops up and community Earth models are right there. And if you also click on computing, community Earth models are right there as well. So we hope that this makes these community models very findable and very accessible to anybody in the world. They're not behind any paywall. You don't need an account to get these things. If you click on the community models link, you'll be taken to the community models homepage. And I'm going to talk to you about this later. This is the Community Earth Models homepage, and you'll see at the middle we have what's called the Community Earth Models widget, which automatically scrolls through all the products we have available and links to the homepage, the web-based tools that we call the explorers, and if they have an archive, it links to their zenodo.org page. So I'm going to go through all of that today here for the community fault model. So everything else now is going to be specific to the community fault model. And I guess the easiest place to start is, what is the CFM? The CFM is an object-oriented and it's fully three-dimensional representation of active faults in California and beyond, because we have some faults in Nevada and Mexico now. It's primarily developed by Andreas Plush, who is the main builder of all the faults. And then my role is mainly with data management and automation and web tool development. But the actual construction of the faults is Andreas and John and their students as well. So you see a rendering here of the full three-dimensional model with some seismicity. We are not the only fault model in California or even the Western US. The most commonly cited models are the Q faults database, which is now being passed on to different states. But this is the Quaternary Fault and Fold database, and you'll see that there are a lot of faults in it. The National Seismic Hazard Model has a simplified 2.5D model, and then the SCEC community fault model is a full three-dimensional representation of faults. Now, all of these are great products, but they were all built for different purposes. So you can think of the Q faults archive as essentially being like an encyclopedia of everything that's been mapped and studied in the field. And so it can be a little bit overwhelming, and we all know that there are a lot of surface cracks that don't, end up being faults at depth. But it's an amazing resource. And so a lot of our fault traces are actually based on Q faults. The National Seismic Hazard Model has a fault section database that's specifically for their hazard model. So in Southern California, it's actually based on the community fault model, but simplified. So the builder of this model would say it's 2.5D because all the faults have a trace that's two-dimensional, but they all just have a single dip angle. In the CFM, and the Q faults database has virtually no depth or dip information. It's just two-dimensional traces. The SCEC community fault model actually isn't represented very well on a map because it's a full three-dimensional model that has variations in down dip, variations along strike, as much variation as the data that constrains these faults can give us. So essentially, we want the CFM to be the best representation of what we think faults in California look like. Okay, so if you go back to the community fault model homepage, this is what it looks like currently. And so what I'm going to show you is these three buttons down here: the CFM archive, the CFM Explorer tool, and the background and context. The CFM archive link will take you to Zenodo and show you where you can download a zip file that contains everything in the CFM. And I'll give you a little overview of what's in there. The CFM Explorer are our web-based tools, and I'll give you a short tour of that. And then the background and context page gives you more information about what the model's based on, what its purpose is, and how we build it. So let's jump into the web-based tools. If you click on that the Explorer link, you'll be taken to an interface that looks like this. And it's a clickable, draggable map, like a Google map. It's based on Leaflet, which is a JavaScript open source plugin. And all the faults are clickable and zoomable. You can also you can load relocated seismicity or your own KMLs. You can change the base maps, and you can even search recent earthquakes, which is really cool. We just added this last year. So if you click on that button, you get a menu where you can query the United States Geologic Survey's real-time database of earthquakes. And it defaults, if you just hit custom, to give you the last year's worth of data. And once you hit enter and extract the data, it will plot it all on the map. And the cool thing is, not only does it plot it on the map, if you actually select the faults, you can hit plot 3D down here and you can see the earthquakes and the faults in 3D with no specialized software. A little interface loads, and I'll show it to you later. It's pretty amazing to have this available with no special tools required. And past models are up here in these buttons, by the way, if you're curious. Andreas Plush is going to talk to you about this a lot more, so I'll be brief on this, but I guess the take-home message here is that the community fault model is not an algorithm. It's a model that's built by humans, and we do use an algorithm now and then, but most of it is actually involving, this is the Ventura Pettus Point fault, and you can see it's involving all kinds of different data. You have a dip angle here that's shallow, then it's steeper, then it's shallower. You have a fault trace, you have some seismic reflection profiles, you have some well data. We try to integrate every kind of data that we can find to build three-dimensional representations of faults. We think that's the best way to represent what faults look like in Earth. The downside is what a lot of modelers want is they want a dip angle and an error bar. When you build a fully three-dimensional representation like that, you can't just say the dip is 45 plus or minus 2, because every one of these patches is actually a triangle. And if you change the dip on one triangle, you'd have a hole in the fault. And so there's a covariance between all these neighboring elements. So how we try to represent uncertainty in the community fault model is by having alternative representations. So where there's significant data to suggest two different plausible representations, we'll put one as a preferred and one as alternative. And they get rated as preferred or alternative based on community evaluations. Now, there are times where we can use an algorithm to do this, and the Harvard team, the Reisner et al., published this. It's a really amazing algorithm. If there's a lot of earthquakes and focal mechanisms and surface traces or ruptures, you can feed all that into this algorithm, and it will build a three-dimensional fault network out of that data. And it worked so well that Andreas and colleagues applied this to the Ridgecrest earthquake sequence in 2019 in California. And that is the representation that's in the community fault model right now. It's quite complicated because that earthquake sequence was quite complicated. And so we do this sort of semi-automated algorithm whenever there's sufficient data. Just know that that's often not the case with many of these faults. For example, there's a significant section of the San Andreas that has very little seismicity on it. Okay, so I keep telling you that the CFM is three-dimensional, but I haven't actually shown it to you. So let me run this animation. This is a MATLAB generated animation, and this script is publicly available on the CFM homepage. So let's watch it. It should go. Notice that this is the Mount Diablo thrust. Now it's going. And all the triangles are shaded by the dip angle over here. And you can see that near the surface, the dips are actually quite steep, but as you get down deeper, the dip angles get shallower and shallower. It's like a Listric fault geometry. So we have dips everything from 80 to 20, and the National Seismic Hazard Model can't represent a fault like this because it simply has one dip angle. But we know faults have geometries that look like this in some cases. So we want to make sure we have a model that can represent faults in the most accurate way that data can maintain or constrain, I guess is the right word. So good news is that in 2026, just a few months ago, we published a paper in the Bulletin of Seismological Society of America, BSSA, on CFM 6.1. And that is the Southern California portion of the latest model. And we didn't include Northern California in this because the Northern California portion of the CFM is actually pretty new. It's only been out for 2 years, and it underwent a community evaluation, which I'll tell you more about. But we hope that people will check out this paper, and we did some pretty interesting analyses of the CFM, one of which I'll show you a little bit later. The current version of CFM is 7.0. It's the first statewide coverage model. You can see we're covering the whole state of California and beyond, some in Mexico, some in Nevada. And this was peer reviewed by a group of experts in 2025, and they provided us a wealth of information about things that we should consider changing or adding, or in some cases removing. It's so much information that we've actually been working on it for the last year and the year ahead as well. So the Northern California portion of the model is going to be changing in upcoming years, and that's what we're currently funded by SCEC to continue updating. This model came with an updated Explorer, which I showed you. The model is released in GoCAD format, and I'll show you more about that later, but we also have a KML file. But overall, we're talking about 556 faults. 113 were new just in version 7. And 39 of those faults have alternatives where there's a significant different interpretation that is geologically plausible. So let's look at that KML file. So KMLs are native to Google Earth, but if you're a QGIS user or any sort of GIS user, you should be able to load these. And this is sort of zoomed in on the San Francisco Bay Area. So we're looking over here at like the Hayward Fault. And if you click on a fault, the metadata from the CFM pops up automatically that tells you all the different facets that sort of help define that fault, like its average dip and its strike, what references it's based on, any notes. These are all attributes in the KML, so if you use QGIS, you should be able to load these attributes in QGIS as well. So we hope this is useful to you. The web-based tools, the CFM Explorer, doesn't actually host every single thing that's in the Community Fault Model archive. So if you want the whole thing, you need to go to Zenodo, and it's linked on the CFM homepage like I showed you. But this archive has everything from version 7 all the way back to version 5.3.1, and it's all publicly available and documented. We try to give like version histories to let you know like what's different about 7.0 and 6.1 as well. So let me show you what's actually in this archive. I think it might be helpful if you're considering using a model like this or comparing to what Japan offers. The root directory of that zip file contains 2 directories called doc and object. The documentation directory has a spreadsheet, an Excel file, and it holds all the metadata. So every single fault has like 25 or so columns of different things that contribute to that fault object. And so what most users want is they want things like surface area or strike or dip. Remember, it's average because the fault is non-planar, or references, like what is this based on? And so those are all in there. The object folder has 3 subdirectories: alternatives, preferred, and ruptures. Each of these directories has all of these subdirectories, but the tree was going to get messy, so I'm just blowing up the preferred one here. And we provide the model in 3-dimensional triangulated surfaces in 4 different resolutions. Native is sort of how we build the model, where the mesh shows you where there's data and where there's not data. I'll show you that in a minute. And then we provide semi-regularized meshes with nice triangles that are about 2,000 meters wide, 1,000 meters wide, and 500 meters wide. So we hope these are ready for modelers to use. We also provide just traces if you want to make a map like I've shown in GMT plain text format, KML, and shapefile format. So all of this is in the archive, and it's freely available to anybody that wants to download it. So let's take a look at the 1994 Northridge thrust fault that made that event that was so damaging to the Los Angeles suburban region. This is a 3D rendering of it using MATLAB, and what you can see, and again, not GoCAD. So you can use not GoCAD to render GoCAD files. I'll show you more about that later. But you can see that there are tons of triangles here in the middle, and that's because that is where Carena and Suppi actually relocated all the aftershocks after the Northridge event to define a complicated non-planar surface. However, dislocation models based on geodesy showed that the fault has to be bigger than this. And so this outer part here is this sort of poorly resolved dislocation model, and that's why the triangles are bigger. So the native mesh has the advantage of showing you where there's data and where there's not data. However, we also recognize that, yeah, if you're a modeler, you're looking at this right now going, I can't model that. Those triangles are terrible. I know, right? So we also make a regularized triangulated mesh. This is the 500-meter mesh that should have pretty close to equilateral triangles all throughout the fault surface. So we hope those are useful to you. And the model is provided in UTM coordinates, so it is Cartesian. Just to further emphasize that GoCAD files can be used by anyone, because the first thing that people hear when they hear GoCAD is their brain immediately says, I can't use that, I don't have GoCAD. Well, the GoCAD software is not free, but GoCAD files are open source, plain text ASCII files. They're straightforward to parse. So this is just 3 triangles from that Northridge thrust that I showed on the last slide. So to define any fault in 3D space, you just have to define the triangles and how they're connected. So each triangle has 3 vertices or points, and then you have to say how they're connected, and then you have a triangle. So this is a text editor showing that there's a header, like with the fault name, the color of the fault, all that stuff, the coordinate system. But then it's basically just a series of XYZ coordinates of the vertices. And then to define a triangle, you say connect vertex 1 to vertex 2 to vertex 3. 1, 2, 3. So you can write code to parse these in whatever programming language you like. Python, R, MATLAB, Fortran, doesn't matter. This is the minimum amount of information required to visualize a 3D surface. And that's why we use GoCAD files, because they're pretty easy to work with. If you have any questions about these or problems, just let us know and we'll try to work with you on getting stuff in a format you can use. People commonly will ask us about fault slip rates. And the community fault model doesn't contain any slip rate information, but SCEC has developed a geologic slip rate database that does. The geologic slip rate database is available through the community models site that I showed you earlier. It has a web interface called the GSRD Explorer, Geologic Slip Rate Database Explorer. And just this past year, we added about 100 new sites to it, and we're going to be looking to update that in about the next month or 2. So it'll be coming up soon. But this is not part of the community fault model, but if you want to know what the slip rates are in California and Nevada, you can look them up right here, and it has hyperlinked references. It's really nice. Every one of those dots on the map is a field-based study that a geologist did to quantify the long-term slip rate of a fault. So it's really nice. So I'm going to end giving you a few slides showing you what do people do with the community fault model at SCEC and beyond. And so this is a paper from my own research group that we published in 2022 in Seismological Research Letters. And what we did is we took the community fault model and combined it with a boundary element method model using the code Poly3D. And we were able to simulate long-term slip rates on 83 faults in the CFM. And meshing this did take quite a bit of effort, but 83 faults we were able to quantify at like 1 to 2 kilometer scale elements, so full 3-dimensional slip distributions. And we compared those to the Uniform California Earthquake Rupture Forecast, sort of expert panel average slip rates, and found that the root mean squared error, was only about 0.4 millimeters per year. So we fit them very well. Even though you say 75% fit isn't good, but the ones that we didn't fit, we only missed them by a little bit. We also compared to all those point-based estimates that I showed on the last slide and fit those within 0.8 millimeters per year, about. So this model does a really good job of predicting geologic slip rates, and of those 83 faults, a number of those faults had no slip rate estimates at all. So this is a really important use of the CFM to be able to provide computational modelers with a full 3-dimensional rendering of faults. Without that, this kind of study simply could not be done. We'd be modeling very simplified faults. Probably the most exciting thing we've done with the CFM is this paper by Walker Evans and others at the Harvard group. And what Walker et al. Did is they looked at creating a statistical algorithm to figure out which, to associate earthquakes with the source fault. And this was published in BSSA in 2020, but we went one step further and we actually have implemented this real time running at the Caltech servers. And so What I want to do is I want to show you if you have a SCEC user account, you can go to your dashboard and sign up for earthquake association emails. And every time there's a magnitude 3 earthquake or larger in Southern California, you will get an email that looks like this, where you have the magnitude, the location, a direct link to the USGS, and which fault the algorithm says is most likely, and then the next couple runners up. So you'll see this is most likely on the Anacapa Doom fault, but 30% chance and 24% it could be on the Malibu Coast fault sections. Those are the same fault, just different sections. Importantly, the code also tests whether it's not in the CFM. So let's take a look at this. This is a movie. So you can click on these. So if I click on, you can see that these are all pretty closely rated. This is my favorite example. This is why I'm showing it. This is the USGS Comcat catalog, and you'll see it has a focal mechanism, and the association service takes that into account. The focal mechanism suggests moderately shallow dip. If you look at the map view, it links to our Explorer tool automatically, and you'll see the earthquakes right here. You think, why is it not associated with this Malibu Coast fault right here? It's actually associated with the red fault. But you can also look at it in 3D, which is amazing, and rotate it around. And what you'll see is that this fault plots below the Anacapa Doom thrust. And you're thinking, but wait a minute, what about that Malibu Coast fault that's sort of right up here? Go back to the interface, turn it on, and then render that in 3D by clicking Plot 3D. And again, all these tools are free and anybody can use them. And you'll see that that Malibu Coast fault is actually truncated by the Anacapa Doom fault. So that's why, combine that with the fact that the focal mechanism suggested a shallow dipping surface. But if all you had is a two-dimensional view, you'd think the association service is wrong. It's actually doing its job quite well. And I should say that the association service was validated on a set of data that was not used to build the CFM. So that's all in that Evans et al. Paper. You should definitely check it out. It's a pretty neat algorithm. We're looking forward to implementing this statewide in California, but there's some IT hurdles that we have to get across first. Okay, and then the final slides are, we actually use this algorithm to assess completeness of the Southern California version of the community fault model. And so we loaded in this very dense catalog of focal mechanisms and relocated hypocenters. And we ran it through the earthquake to fault association algorithm, and all the colors here of dots are color coded to the faults. So any colored dots are associated with the fault, and any black dots mean they're not associated with the fault. And so what you can see is the vast majority of the earthquakes are associated with the CFM fault, which is good. That means that the model is doing a good job of explaining the seismicity. Histogram-wise, what you can see is we split it up between magnitude 3 to 5, and the CFM 6 outperforms the CFM 5, shown in gray, but it also outperforms the National Seismic Hazard Model fault system section database. Magnitude 5s to 6s are here. It's the CFM 6 is the only model that associates all magnitude 6 plus events. The other two models miss 2 of them. And overall, for all magnitudes 3 and above, which is what the algorithm was designed for, you see that it gets about 90% of the events. So we think this means that, at least in terms of historic seismicity, the model appears to be pretty complete. It doesn't mean that future seismicity will be predicted by the model, because we all know that future seismicity can sometimes pop up on faults we didn't recognize. But in terms of historic seismicity, it seems to do a very good job. So I will end by thanking all of the people that helped us evaluate CFM 7. We're working on your great suggestions, and in the next year or two, we should be releasing a CFM version 8. And yeah, we hope that you use it and that this was interesting and helpful for your research efforts. Again, my name's Scott Marshall. Let Andreas Plescher I know if you have any questions about the community fault model. And I think Andreas is going to tell you more about how it's built. Thanks again. Bye-bye.